Hello again. What has happened since last time? Many small things. On the one hand, I extended the power supplies a little bit to cover some more losses. Now I've got up to 90 volts and 90 amps, which means I can cover 8 kilowatts of losses. Furthermore, I turned around the entire test bench. The machines as well as the power electronics, having better cooling conditions in general and also avoiding thermal shutdowns of the power electronics, which appeared more often in the past when I increased the overall power of my system. Then I kept on modifying the machines, the rotors of the machines. Now I've got for both 48 small heat sinks attached to the rotor, as you can see, and I also tried out a slightly different design. That's how I started with a radial fan design over here with those heat sinks, and I tried a real blade design, but unfortunately it wasn't as helpful as I hoped for. Another modification was done over here, as you can see. The original design with the small heat sinks, which looked like that, which I called Hedgehog Design, make a guess why, was done by rotating those small heat sinks a very little bit. That was good because it helped an airflow in general from right to left over here in that picture. So in total I've got an airflow through the machine from front side over here to the radial fan on the other side, and also outside the machine that direction of airflow is supported. So that's what it looks like right now, and the measurements done have been satisfying so far, and now we're coming to a live demonstration. I reached meanwhile 10 kilowatts mechanical power continuously, which means in my case 14 minutes. That's the standard time I'm measuring, and within those 14 minutes the machine heat up quickly because the thermal time constant of the machines gets decreased. You know, if you lower a thermal resistance, which happens definitely with those heat sinks, but you do not, thanks for the power supply making some noise, but not increasing that much weight, so thermal capacity stays the same. That means you're shortening the thermal time constant. The machines heat up quickly, but they reach their final temperature soon. As I said, I was able to have 10 kilowatts over here continuously, and that's also planned right now to give you just a live demonstration. Everything is set up over here. The brake of the generator is pre-adjusted to a certain value. Over here you can see the current flow into the power electronics of the motor. We're running the system with 89 volts, and if I just apply some throttle, the system starts running. The generator is already active. That's what you can see over here. We're putting some amps into the system, covering the losses, and the current into the machine is much higher. Additionally, you've got always an eye on the temperatures of motor and generator of the stator windings. And now I will apply a lot of throttle, having 130 amps over here, which means we're putting in almost 12 kilowatts of electrical power, having almost 10 kilowatts mechanical power. I will stop talking. You won't hear me anyways. It makes a lot of noise and also some vibrations, lots of airflow, so quite entertaining in here. Here we go. Okay, that's it. Temperatures increased a little bit as expected. You can still easily touch the machines. Yes, they are warm, and maybe you have recognized it. There was a current flow of 45 amps into the system, which means we've got losses 45 amps times 90 volts. I don't know, but with the 130 amps for our system, it's a typical efficiency, overall efficiency of 82%, I would say. The speed was at 3500 RPM, which was displayed over here, and you can backwards calculate the torque, which was around about 20 Newton meters. I also made many more measurements with different speeds, different torque constellations, trying to find the optimum highest power operating point, but that's almost it. 10 kilowatts at different constellations of speed and torque. You always suffer somehow either higher currents, higher temperatures in the stators, or at less speed you've got not such good cooling conditions, and quite many dependencies coming in, because the losses in the rotor depend a lot on speed but also a little bit on torque. And the losses in the stator mainly depend on current flow due to torque requirement, but the cooling conditions highly depend on speed, most likely speed squared if you've got such a radio fan design. But anyways, now I've got 10 kilowatts, and if I operate both machines as motor, I've got up to 20 kilowatts, and 20 kilowatts is something, I think that's enough to make a small vehicle moving. Peak power I achieved over here with that setup was more than 200 amps flowing into the system. Then I reached the limitation of 8 kilowatts losses for both machines, motor as well as generator. And more than 200 amps at 90 volts is almost 20 kilowatts electrical power put into the system at an efficiency of close to 80%. Sounds like maybe 17 kilowatts mechanical power. Pretty satisfying. And I also saw on YouTube some videos with brushless DC motors claiming 30, 35 or even 45 kilowatts. Sorry guys, I completely doubt those results. Looking at their setups, cable sizes, capacitors, power supplies, power electronics, no chance to have those powers for those setups over there. So having 20 kilowatts in such a setup is pretty amazing, and you can feel the power. Alright, so far, meanwhile I started thinking about a drive unit for a small vehicle, and the testing of the machines of those Revolt 160 Pro is more or less done right now, and I will concentrate on some mechanical parts. Drive unit, dual drive unit for a small vehicle, and next time in a couple of weeks I will introduce that drive unit and also the hot candidate for the vehicle to you guys. So far, stay tuned, see you next time, goodbye.